plus 1 I will take plus 1.5, so that the values it generate will include minus 1 and plus 1, the boundary values. Is it clear? Yeah, so because the boundary values also to be included, we are just extending the boundary little, so that algorithm will get the boundary values also for influence the range. That is why. Okay. Yeah, it can be any number. It can be any number, not necessarily 0.5. So, but we are taking any closer range. That's it. So, not necessarily 0.5. So you should keep this also into account. That is the range. Now, when you're calculating the number, you have to tell the steps. You will be telling the step value. It should be greater than the step value. See, I'm telling I'm starting minimum maximum in steps of 0.5 means the value added should be greater than or equal to 0.5. Okay, then only that it will cover it. That you should take care of. You got it? Yeah. So any number means it should be that step more than that step, equal to, greater than or equal to the step value. Okay. So the next linear machine we are going to see is the perceptron. Sorry, the spelling has been got wrong here. Perceptron, it's not perception. Anyhow, it is doing some kind of perception only. So the perceptron is the basic building block for any neural network models. I think would have gone through those things. Anyhow, I'm just restating things. So here again, as I said, because it is a linear machine, classification machine, it has the same set of things: the decision rule, the loss function, the gradient loss, the update rule. So of its parameter. So in the case of perceptron, the parameter to be learned will be the weight vector. So the weight that is given to each connection of the perceptron, and f will be the threshold value. So the threshold value which processes the sum of product of the weight and the input data. And the loss function again. So it is don't get carried away by the equations and all. It is basically the same. So f of w prime xi is nothing but the output produced by the perceptron, and yi is the desired output. So the same thing only we are doing with regression also. Whatever output the perceptron computes, that is subtracted from the target value. The thing is, we are not taking the entire thing as a loss. We are taking as a proportion of the product only, w prime xi. Usually you call w prime xi as a net value, the product of the weight and the input connection, input and the weight of. So that you are taking as a proportion of this. The loss is taken as a proportion of this weight and input data. So that is the difference here. So this will be the loss function used, and then you are calculating the gradient for this loss to find the rate of change of the loss with respect to the weight vector. You compute the gradient, and the portion of the gradient loss is used for updating the weight. So all these things are basically same, with some minor change in the way things are computed, how y is computed, how loss is computed, how it is added, etc. So if you want to get a direct solution for this, then we have to solve this inequality. Solve this inequality for w, because we already know xi and we will know yi. So you have to compute find value of wi such that it satisfies this, satisfying this inequality. So when the algorithm does give the correct answer, always this inequality will be less than 0. So for example, if the desired output is -1, now the perceptron's output is also -1. Perceptron output is f of w prime xi. If both are -1, what will happen? So here first y is -1. So minus of -1 will be +1. 1 into -1, it will be -1. So it is less than 0. Like that, if the desired output is +1. So this functional is in this function we are telling that positive class is 1, negative class is -1. So if it predicts positive class, suppose y is 1, and then the algorithm the perceptron also predicts 1, then minus of y will be -1 into 1 will be still -1. So the value will be 0 only, less than 0 only. But if it makes a wrong prediction, suppose the actual target is -1, but the perceptron produces +1, what will happen? So minus of -1 will become 1, and 1 into 1 will be 1, which is greater than 0, which means that the inequality is not satisfied. So what this inequality tells is you have to find the value W such that always the product error will be less than 0. When the product error is less than 0, the data will be correct. So that is the inequality. Again, we are taking this inequality based on the functioning of the neuron perceptron only. Okay. So this is the case. So the decision rule, loss function, gradient loss, update rule. Okay. So just thing, and I will just go through this just to show the way this perceptron is built and all. So I think you would have done it in the neural network course also. So basically the perceptron contains two units, the processing unit and the threshold unit, activation function you call it. Usually you call this as the net value. And I told you like the intercept and all. So the bias value for a perceptron is nothing but is modeled as a fixed input and the corresponding weight. So bias value is modeled. So it will be part of the input only. That is why we do not explicitly show this bias. So this will be as like a part of input, and this will be taken as part of the weight vector. So in this fashion, this perceptron is modeled. So whatever input is given from x0 to xn, it will be multiplied with the weights and added up, and that will be the C value. And from the C value will be given as input to the activation function. The activation function will produce the respective output. Is the slide visible, students? I am getting some disturbance here in my system. Is it visible? Okay, fine. Okay, so now the activation function. So we saw that a function calculates the output based on the sum of product of the weight and the input. There can be different activity. In fact, any function which gives a real value output can be used as an activation function. But based on experimentation and all, they have come up with some useful activation functions. The tanh function, which is hyperbolic tangent function, rectified linear activation function, logistic activation function. These are some functions, sigmoid functions, softmax function. If you will be seeing those in the deep learning networks and also these are some functions that could be used here. So the hyperbolic tangent function provides an output of this format. So you based on the input, the output will vary from -1 to +1. So wherever you have a classification problem where you have 1 and -1 as the class labels, you could go for a tanh function, and it gives a real value, which is the probability of the classes, whatever value. Suppose if it gives 0.91, which means that the probability of the output 1 is 90%. Like that, it gives the negatives. In the negative range means it is up to. So based on that, the algorithm we will decide like whether it is a positive class or the negative class. And the rectilinear function, for negative values, it will output a 0. And for positive values, it will give a linear output based on the input value. So it will just replicate the input value. So this is known as ReLU function. ReLU function has a wide variety of applications, particularly in convolution neural network. So every convolution stage will be followed by a ReLU layer, ReLU function layer. So it is used for introducing non-linearity. So it clips the negative portion and it just gives the output with respect to the positive portion. And then you have the logistic function. So logistic function, it is again at a sigmoid function, an S-shaped function, but it varies from 0 to 1. Instead of -1 to 1, it varies from 0 to 1, and it has a very smooth transition. Again, this also will give some kind of real value, which can be taken as a probability so that you could come up whether it is positive case or negative case. So these are the basic functions, activation functions used in perceptron. And this is how the perceptron works, a basic simple example. So you have given the weight as 1, -0.5, 0.25, and the bias value is -0.5. And the inputs are 1, and for X we are giving -0.5, which is fixed input. As I tell, the bias value will be a fixed input. This will be the input vectors. So -0.8, 0.2, and -0.4. So what it does is it multiplies the weight with the input vector. So 1 into -0.5, that is -0.5, and then 1 into -0.8 here, -0.75 into 2, and 0.25 into -0.4, and it gets the output. So the net value or C value is -1.55. Now, if suppose the activation function is a tan H function, it will compute the value of -1.55, which is -0.91, which means it will take it as -1, the negative class. So in this fashion, the perceptron operates. Okay, so we will see an example of the perceptron. So though perceptron, it is having only one node and the input features, still it can be used for performing a classification process. So we will move on to. So you can choose the perceptron underscore tr file. Okay. So you can run as I execute, as I explain, but as I said, it is time for me. It is little to take up some time. So I'm just showing the already running. You can compare and we can see how. Yes. So again, we are using the iris dataset only. Iris dataset. So we are importing the NumPy package as NP and loading the iris dataset, and then we are going to use a perceptron now from the linear module. So we are loading the data set and then fetching the data part. So the data part will have the 4 features. So the first 10 records is being shown here. So we have already seen the data set in the previous exercise also. Here displaying the names of the target. So Setosa, versicolor, and virgin color, the 3 classes. Now this shows the features names. So what all features? The 4 features: sepal length, sepal width, petal length, and petal width. So this are the 4 features it is showing, measurements of this. So the next coding section displays the target values. As I said, the target, it is like it has split the data, 150 data into 50 data each. The first 50 record belongs to first class, the 0th class, Setosa. Second 50 records belongs to versicolor, like that. So here I am just displaying the first 10 target values. So it is showing all the values as zeros because it is the first 50 will be belonging to the 0th class only. Here picking out the last two. So in that I have showed a different way of doing things by using the array. Here we are using a vector notation. So the second, and I can pass it as a tuple, which vectors I need. So in that case, we took 0 and 1. So here we are taking 2 and 3. That is these 2 vectors, 2 and 3, the last 2 columns. So I'm just displaying the first 10 values for the last 2 columns. So we are going to make the prediction using the last 2 columns here. So if you execute, it will just display the last 2 column values arrays. Now we are making it as a binary classification problem because to perceptron it will tell whether 0 or 1. It is a single node, so it will be able to tell only either 0 or 1 or 1 or -1. If you are taking bipolar outputs, the class will be either 1 or the class will be -1. So here we are going to use 0, 1 classification. So what we have done is, I have taken the first class as the primary class. That is, all records belonging to Setosa will be marked as 1, and all other records belonging to versicolor and virginca will be marked as 0. So in that way, I am making this as a binary classification problem. So for that, I am changing the target value for the first class to 1 and the others to 0. So this is done by using this function. So iris.target means we are checking whether the in each record it will in this thing it will check whether the each record of iris.target is equal to 0. If iris.target is equal to 0, then 1 will be output to y. If iris.target is not equal to 0, then 0 will be output. So in that fashion, I can create an array of y which will contain 1 and 0 only. So 1 will belong to the 0th class. So now this has to be converted into, otherwise it will be kind of object type. So I'm converting it into an integer values. So for conversion of integer, use the as type function, and numpy is int8 representation. So it will use 8 bits. So you have a different 16-bit, 32-bit representations and all. So we are just a simple problem here. So we are using 8-bit representation. So converting the output to 8-bit. So it shows ones for the first 50 records and zeros for all the 100 records. So it has become a binary classification. So if it belongs to the Setosa class, it will be 1. If it belongs to versicolor and virginca, then it will be 0. So if you just printing this will help you to understand how the target has been modified. Then we have the model train test split to split the data set into training and testing set. So the X and Y which you have created, we are splitting it into train set and the testing set. So now here I'm just printing the records, that is the shape of the training data and testing data. So the initially the record was 150, and training data we are splitting into 75, 80, 20 percentage. So 80% training data, 20% testing data here. So 120 and 30 it has been split. So now we are going to find the number of values in the test data. In the training data we saw there is 150. So now when after splitting, I need to know how many records belong to class 1, how many records belongs to class 0 in the test data, so that I can make comparisons and all. So you have 30 records. Out of these 30 records, how many belongs to class 1, how many belongs to class 0. So that I can do because there are only 2 classes. I can call the unique method np.unique and give that y test value. And this return counts will tell how many class belongs to 0, how many class. Otherwise, it will just display these 2 values. The unique values are 0 and 1 only. But I also need the count. So I am just set this parameter return counts to true. So now it says there are 19 records belonging to 0th class and 11 records belonging to 1 class. So we know the distribution of the class here. So how many class present in the X test and that is in the Y test. So now the standard things, we are using the standard scalar. So standard scalar objects are created, one for the training data and one for the testing data. And then that both are transformed. So training data is transformed between 0 to 1 and testing data is transformed between 0 to 1. So now the training data after transformation. So you saw the initial value here, it was in this range 1.4, 1.0, 0.2 and all. So after the standardization, these are the values you get. So now the perceptron. So perceptron object we can create by using the perceptron constructor, and we are giving the random state for as I said in the previous case. So this is for fixing the seed value for shuffling process and all. So we are fixing it as 0, and the number of iterations you need to tell how many times the algorithm has to train itself. So for the entire record set. So if it goes through all the records, it will be 1 iteration. So how many times it has to repeat until the weights are fine tuned. So here we are telling that 10 steps. So with 10 times the algorithm has to iterate. So after fixing this parameter, you can call the fit functions. Fit function is commonly used for any algorithm for the training process. So fit function X train and the Y train. So when it calls this, automatically the model will be built, and it is displaying that perceptron model for a maximum iteration of 10 has been built. So now you can use this model to predict the test value. So you call the predict method. Again, this is common for any classification algorithm. You call the predict method and pass the features, test features. So the predictions will be given here. Y value will be given here, predicted Y value. So now we are using the classification report and the confusion matrix for the prediction process. So confusion matrix I had not used in the earlier case. It will show like how many from each thing, how many has been predicted. Here it shows a percentage. Here it will show the exact value in confusion matrix. So if you pass the Y test and the predictions, it gives the. So what it tells is, we saw that there are 19 records belonging to the 0th class and 11 records belonging to the 1 class. So it has predicted all 19 records correctly and all 11 records correctly. If there was any mistake, then these two things, the diagonal will show the correct classification, and these are wrong predictions in the opposite direction. So we see that both have been predicted correctly. So if you print the classification report, it tells that it has a precision of 100%, recall of 100%, everything 100%, because it is a very simple. So you can see that a single node, a perceptron, which is just a single node with the proper training by using the weights and all, it is able to predict 100%, which the linear regression was not able to do. We had used linear regression for predicting. Of course, we are predicting here only binary class, but still it was able to predict 100%. So this is the significance, like how when the power of the perceptron, though it is very simple, it has sufficient power for doing some basic predictions and all. Is it clear, students? Anything you need? Have you executed this? Can I proceed with the content? Fine. So the next thing we are going to see is logistic regression. So logistic regression, again, the 4 components here. There is no simple trivial way of finding the verification. So we have not included that, but these are the 4 basic steps. Decision rule. So decision rule, it uses an activation function which is tan h instead of the normal regression. Regression will just do the dot product of the weight and the, that is the parameter and the x value. Here you are using a tan h function to do the things. So then the loss function is a log. We are taking the log of the loss. So it is log likelihood. It calculates the log likelihood loss, and that is used for the loss function. We will see why it is using this. And then the gradient of this loss, calculating the gradient, the rate of change. And this gradient, a portion of this gradient is used for updating the parameter value. So this is the difference here. So the decision rule is a tan h rule, tan h function. It uses an activation of tan h function, and the loss function is the log likelihood loss function. Other things, the loss is you calculate the gradient of the loss and then give a portion of it to modify the parameter. So logistic regression is used for basically predicting binary classes. So where the target has only 2 class values initially. So an yes or no can, like predicting a disease, whether the person has the disease or not. And the output it gives is a probability. The tan h function, as I said, it gives the probability. 90% the person has a disease, 10% the person does not have the disease, like that. So the output will be a probability of occurrence of that particular event. And later, this probability was used for further extending its functionality. Like you have 3 types of logistic regression. So what we saw was the binary logistic regression, where you have deal with an yes or no question or a binary class. And multinomial logistic regression, you have the class, different values for the same class. That is, I want to predict different types of wine. So it is the wine class only, but you have different categories. Even if I say I want to predict different categories of dog, I will have a dog variety called Rajapalayam. I will have Alsatian, like that. So I want to predict different categories of dog. So like that. So that is multinomial labeling. So if I want, I can use logistic regression. It will give a probability of the different categories. What chances are there that it belongs to a particular category? And if the multinomial values is an ordered value, then you call it as ordinal logistic regression. So like rating a movie, rating a service. So everyone, from Amazon to all people you deal online, you get a message asking you to rate. So that they analyze and they come to know whether the customer is satisfied with or not. So that is a kind of ordinal logistic regression which will predict based on some features whether what will be the rating for this service and all. So they use it in such purposes. So that is ordinal logistic regression. So basically, as we said, the output is a probability. So we'll be predicting where a class is one. We take the binary example class here. So when a primary class will be taken as one. So the probability of getting primary class given the input observations that you calculate using the tanh function. Now the negative case is just subtracting one. So probability, you know, so the addition of both the probability should be one. So you can get the negative case, the second class probability, by just subtracting one from it. Now this can be expressed as a learning formula in this fashion. So the value probability of one class into probability of zero class to the power yi and 1 minus yi. Because now if I say the desired target is 1, then what will happen is this term will become 0, because 1 minus 1 is 0. So anything to the power 0 will be 1. So you will get the probability of the one class. Like that, if the probability, if you y is equal to 0 means, then this will become 1, because yi will be 0. So this will become 1. You will get the negative probability. So we are dealing with this kind of equation. This will be the learning rule. So to calculate the loss by using this learning rule, because you have power multiplication and all, they are using log to simplify the computation. Log will convert it into a kind of summation. So you are taking the log values of this particular computation. So that is why we call it as the log likelihood. So this log likelihood will tell the chances that the prediction belongs to a particular, the observation belongs to a particular class. So now we want to find the negative loss, because the loss value, yeah, we do not want to find the goodness value. We want to find how bad it has performed. So that is done by getting the negative of the log likelihood. So the negative of log likelihood will give you the loss value in a sense. So that is why we are using negative log likelihood for logistic regression. So this will be used for minimizing the loss. So that is how this uses this particular function. So logistic regression, again, we have an example. I do not know whether time permits. So I will, you have the example there, but the same kind of execution only goes. You can just see the operation. I will continue with the other portion. Maybe if at the end, if I have time, I will just discuss it. Show the execution part. And then you have so we saw three methods. So this is the generalization. So all methods use gradient and all methods use the supervised learning. So what we find in common is you have a decision rule. So decision rule of the from output is equal to some function of the parameter and the input variable. So f can be any function. So it depends depending upon that the method varies. And then you calculate the loss function. The loss function is a measure of the distance between the output computed by the algorithm and the actual output. So it gives the discrepancy between 2 points if you take it as A and B. And gradient loss, you find the rate of change, how it the loss varies with respect to the change in parameter, and use that information. Yes? Anything? Any? I heard some voice. Want me to? Can I proceed? Okay. So now these are the basic things used. So the question is based on the what kind of thing use, what function architecture, that is what a function you are using here, and what will be the loss function, and how the algorithm can be optimized. So we can do, because it involves some kind of matrix operations and all. There are optimization methods where you can compute things in a shorter way. So how things can be optimized. So these are the crucial things that we have to decide when we go for this linear learning machines with the gradient descent loss function and supervised learning. So what are the limitations of these methods means? So we saw that actually we saw the mappings and all, the graph and all in the examples. So the clusters are formed. So we need to find some kind of line or curve which divides this into halves. So that is called as linearly separable dichotomies, two classes that could be separated in the space, data space. So you should be able to draw a boundary. That is the primary purpose of a linear classifier. So what happens is when the number of records become huge and the number of features present is less, this division is very difficult to achieve. So the probability of a linear this is known as Cover's theorem. So when the records grow, number of instances is high, but the number of features used is very less, and you have a binary classification, two class classification. So what happens is you have 2 power p possible chances, because every record can be feature can be classified into 2 class. So that many chances, but you have only n features, and using that n features, predicting all those possibilities is very tough. So what they say is the probability will approach 0 here. So the chances of getting the correct kind of decision will be 0 when the number of sample increases very much higher than the features available, number of features used for classification. So this I can show you here. Uh, okay. So you can open the perceptron odd even decimal underscore PR. So it is a very simple example which states that how classify whether a number is even or odd. So we are going to use a perceptron to classify whether a number is even or odd. For that, I am giving a set of numbers as input and trying to train it. So what I am doing here is I am creating the as usual NumPy package import and the perceptron model, and I am creating the numbers. So I am going to 1000 numbers I am creating. The first 10 I am displayed 1 to 1000. So I want to identify this whether this number is a odd number or even number. So that is the function of the perceptron. So what I am going to do, these are just checking the shape. So what is the shape of x, and because we have to give it as an array, the x is here is a vector. So that has to be converted into a matrix form. For that we are using the reshape method. So the reshape will add one more dimension. It makes it like a matrix. So it becomes an array of values. So that we are doing, and then we are I have to create the target value. So for the 1000 records, I'm just dividing the number by modulus 2, because even numbers are divisible by 2. So modulus value will return 0, remainder. So whether the number has a remainder or not. So if it is an odd number, the remainder will be 1. Even number, the remainder will be 0. So this is how the I'm creating a y variable which tells me whether the numbers are odd or even. So now I have the x value, I have the y value. So I'm training it using the perceptron. So I'm training it using the perceptron, and now I want to test the perceptron. So I have trained it from 1 to 1000. So here I have given an input value of 101. So 101 is an odd number. So when I give this 101 as input, it should report 1. And when I give even number, it should report 0. But if you execute the program, you will find that it will just output only zeros, or the other way around. So even though we are giving the entire number, why it is happening is the number of records is huge, whereas the feature is just a single feature. From this single feature, the perceptron is not able to understand the difference between odd or even. So it is happening like this because of this. Now, this can be avoided by using a method here. So when this problem occurs, this can be avoided by using increasing the dimension. So by making the number of features large. So what they do is they use a vector function. This function can be any function. I will show like for that our problem how I am doing this vector function. This vector function will increase the features used in X to it will multiply the feature. So this is not adding any additional data. It is only modifying the look of X. So that you should keep in mind. We are not changing the value. The value is same, but we are modifying how the value looks by adding some additional components. Now using that additional components, the prediction is done, and then the value is computed and the errors are calculated. So this will help us to perform the classification properly. This is known as increasing the dimension for linear machines. This will help you in getting a satisfactory result if the machine is not performing well. So we will see that here the example program. Now you have another program called as even perceptron odd even bin binary. So here I am doing the same task. But what I am doing is I converting the decimal number into binary number. Now what happens is I am converting into a 32-bit binary number. So 1 will be changed to 00001 like this. So now the input feature has increased. you have 32 input features. I have not changed the value. The value is 1 only. The value will be 2 only, but the representation I had changed. By changing the representation, I have increased the number of features. So I have made it as binary numbers. Now, if I, by using the binary numbers, I am performing the same operation, same thing I am doing. Modulus 2, I am getting the target 1, 0 and all. And then I am fitting the perceptron by using the binary features. Now, if you see, the algorithm will work. Even it will work for values greater than 1000. If you say 10,000 like that also, it will work. But not all values. The accuracy is not 100%, but it is far better than when you are given the decimal value. So this is one example of the dimensionality increasing. Is it clear, students? You are able to understand what I am telling? The change in representation and all, we have to increase the number of features. If you increase the number of features by changing the representation, then in such cases, the algorithm will be able to better perform. Are you getting the point here? You can execute and see how it performs and all. The idea is I'm telling that method. So what we have to do when we have difficulties in finding things. Is it clear? Can I proceed? Can I proceed, students?
Yes, sir.
Okay. So this is what thing. So one of the techniques. So the limitations to overcome the limitations. These are not again. So even in the simple case like XR, the points are like this. So in this case, you will not be able to draw a single line which will separate. So these are some problems. Which last step in which thing? Okay, okay. Just a second. This one. Is this step you want? Yeah. So the input, no, I have created the model by using binary representation. When I want to check whether a number is odd or even, I have to convert it into binary because of time constraint. I have, okay. So this I have created a function here. Cbin is a function which will convert decimal value into binary value. So when you pass a number to this function, the function will convert it, the decimal value into a 32-bit binary value. So this function only I have used here for converting the 1000 numbers to binary value. Like that, after training, when I want to check a number, I have to convert it into a binary number and then only give the input. So that is what I am doing it here. So I am converting the number into binary number. Then I have to convert it into a matrix representation. So the input should be a matrix. So I am converting into a single column 32-bit value and that I am passing. So when I pass this in this format, it will give the output because it is operating with binary numbers. So here this step, it uses the cbin function to convert the decimal number into binary number and then reshape it into a matrix format and then give the input to predict function. Is it clear? Yeah. You can just go through the coding also afterwards also you will and okay, so in this fashion you can do. And another problem here is this non-linear problems. Non-linear problem, you will not be able to get a single line to divide this space into two equi-spaces, class spaces. So that is a traditional problem is XR problem. XR problem, you will have 0, 0, 0 and 1, 1 also 0. Whereas 0, 1 and 1, 0 will be 1, 1. So the points will be similar to this. You will not have a single line to divide it into two classes. So that is other kinds of problems that you face in the case of linear classification. So one method to do this is by using the increasing the dimension. So by increasing the dimension means not adding some spurious data. adding your one. You should not do that. You have to transform it into a fashion that additional features are present, like how we converted decimal to binary. So in this fashion, it can be done. So this kind of thing, this is what happens. So now this is a data which cannot be divided by a single line two dimensionally. So when I increase the dimension, I will have the representation like this. So where I can create a plane that will divide this and this. So once the data has been lifted to a higher dimension, we'll be able to use a linear classifier only to divide this data sets into two classes. So this can be done by polynomial function also. So polynomial expansion. Polynomial expansion is, suppose this is the input value 1, x1 and x2. Then you can take the product of this, dot product of this, cross product of this. So 1 into 1, 1, 1 into x1, x1, 1 into x2, x2, like that. And you create a set out of it. So repetitions are not done. So you have 1, x1, x2, x1 square, x2 square, x1, x2. So by performing a cross product of the input vector, you can increase the dimension. So this is another technique used for increasing the dimension. So it will increase the dimension space to this format. From n, it will increase to n into n plus 1 by 2. So that is, if for 3 input features, it will create 6 input features. So 3 plus 1 is 4. 4 divided by 2 is 2. So 3 into 2, it will create 6 input features. Like that. So these are some methods used to increase the dimension and thereby make the linear classifier classify things even in non-linear cases. So this kind of functions will help you in doing classification of such kind of data spaces where you cannot have a linear thing when the data space is conic, ellipse, parabola, hyperbola and all. So once you lift it to a higher dimension, you can use standard linear classification algorithm like perceptron, linear regression and all, logistic regression to classify. See, problem here is increasing the dimension will increase the complexity of the problem in terms of the feature as a function of the feature. So when I say d is increased to some value 3 or 4, then if n number of features you have, then the complexity increases n power d. So that is the problem here. So when you then that many number of parameters, the algorithm has to learn. So it will increase the complexity. So for example, uh, if you take a digit that is handwritten digit, so image processing is one of the main things used in deep learning and all. So you have a 16 cross 16 pixel images, and if the number of variables is 256, if you multiply, now if the degree is 2, if you want to lift this to a higher dimension, then the values will be 32,896 variables. If you increase the degree to 3, it will be 27,96,160. If you increase the degree to 4, it goes to a very large value. So this is how exponentially it increases. So the complexity increases. So using the degree can be used for simpler problems, but for complex problems, it will be still a crucial thing. So other techniques are like creating bumps. Bumps means, so you can have a problem space where you will have one particular point which is the solution. So to reach the solution, they create a function which will produce values like this in the data space, a hill value like in the data space, so that ultimately it will come to one of the solutions. So this is called as bumps. And for that they use Gaussian function. For classification, they use Gaussian function. And for regression, they use wavelets, sine functions and all. Again, this is affected by the number of features used. So it is exponential in the number of features. So if the number of features is high, then this will lead to a high complex problem. So the most favored techniques is the kernel techniques, which is used in one of the crucial machines known as support vector machine. The kernel is nothing but a function like what we have seen earlier. So the function can be a radial basis function where it computes. The purpose of kernel is to lift the input data to a higher dimension. This lifting is done without making any computations in the higher dimension, to state it simplistically, not going into the mathematics of it. In other methods, you have to manually lift it to a higher dimension and perform the computation in the higher dimension, which increases the complexity. But in the case of kernel functions, the kernel function will be able to compute the values in the higher dimension without actually making the calculations perform in that fashion. So it is able to do the things efficiently. It is able to efficiently move on to a higher dimension. So the input data is given to various kernel functions, and the kernel function will increase the dimension and gives the respective vectors that will be used for the classification. And this is the primary method used in support vector machine, which is termed to be a good classifier. So this the basic idea here is it simplifies the computation by using a dot product, which will raise this to a higher dimension. So this is called as the kernel trick. So that's why we are using kernel functions. You have different kinds of kernel functions that could be used. Use kernel functions in SVM to lift it to a higher dimension, and then you use the hyperplane to divide the data into different classes. So in the XR problem, to show how it happens, so this is the XR problem. You have the different classes. Now a single line cannot be drawn to differentiate it. Now what the kernel does is it will lift the values based on its characteristics. So now you see these 2 points lie at the bottom and these 2 points lie above. So by having an additional dimension, you are able to lift certain points based on its characteristics to higher. Now you can draw a plane here. You can draw a plane here which will divide this from the data. So this is known as the kernel trick, and it is used for solving the previous kinds of problems here. And some examples of kernels: quadratic kernel, how it operates; polynomial kernels, you have Gaussian kernels. You have, so Gaussian kernel is the more widely used kernel in SVM, radial basis function. So these are some types of kernels that could be used to do this, achieve this functionality. And the next thing is sparse basis function. Sparse basis function, what we do is you take the data set and cluster it into groups related, and the center is taken as a reference point for building the kernel function. So the kernel functions are not built over the entire data, they are built over clusters. The clusters can vary from U to some defined clusters. We can have k value, we will fix at 3 clusters, 4 clusters based on the problem, and the kernel function will be used operating from the cluster. So this also can be used as a kind of discriminant function for computing it in a higher dimension. And other thing is random directions. So random direction is using some classifiers, multiple classifiers to divide the space into different areas. So instead of, if you take here, though it could not be separated by a single line, you can use double lines. If I draw a line here, if I draw a line here, then the values between those 2 lines become one class. The values outside these 2 lines will be the other class. So like that, I can create a multiple divisions. They call it as piecewise linearity, using multiple linear classifiers. That is what you are doing in a neural network actually, multi-layer neural network. Each layer will create a division. So what happens is these divisions will be able to divide the space into different classes. But when the number of classes is huge, again it will lead to some kind of complexity. But still this can be used for finding or classifying when you cannot use a simple function. So these are methods used to overcome the limitations in linear classification as such. So with this, we end this session here. Um, you do not need Torch 7 because it is for the entire module, which will be continuing in the afternoon. For this section, whatever things I have given in the example program, NumPy and sklearn, those module, those things is sufficient. You can check it out. I would like to stop it here. Now, if you have anything to ask me regarding the entire content, anything, I will be able to tell you. Any doubts, any questions? I was not able to execute that logistic regression and all, but I have given the problem programs. You can try it out and see. So these are some of the, because why when you understand these concepts, you can fine tune the algorithm. So one category is you apply existing algorithms on a problem and find the solution. Another category is you want to modify, tune the algorithms. If you understand the basic functionality, then you can create these functions, code this function, create this function, and use these functions to modify existing structures also. So you can come up with some new structures and all. So that is the basic idea here. So you can go through the whatever I have said, the example programs and all. If you have any doubts, you can ask me. or even in future, if you have anything to clarify, you can always mail me to my mail ID. Okay, ma'am,
Yes, sir.
can we end, ma'am? I think they have nothing.
Yes, sir. Yes, sir. Sure. So, sir, you have a session, like you're continuing after the lunch break?
No, ma'am. I have completed my module full.
Okay, okay, sir. Thank you, sir, for your wonderful session on deep learning. So, dear participants, we can now break for the lunch and come back by 1:30. So, I'll be posting a link for feedback and quiz in the chat box. Please fill that. Dear all, session starts in a while. Um, you can extend your lunch break till 2 o'clock. So a speaker to next session will be joining at 2 o'clock. So we'll meet at 2 o'clock. Welcome, Krishnakant sir.
Thank you, ma'am.
Shall we start the session?
Yeah, ma'am, we can start.
Thank you, sir. I request Shruti, please introduce speaker.
Yes, ma'am. We have Dr. Krishnakant Singh, who is a senior member of IEEE. He is working as a professor in computer science and engineering in Jain University, Bangalore. He has acquired BTech, MTech, PGD in machine learning and artificial intelligence from IIIT Bangalore and PhD from IIT Roorkee in the area of image processing and machine learning. He has authored and co-authored more than 70 research papers in Scopus and SCIE indexed journals of high repute. He has also authored more than 25 technical books with highly reputed publishers like Elsevier, Springer, Wiley, and CRC Press. He is acting as associate editor of Journal of Intelligent and Fuzzy Systems, IEEE Access, and guest editor of Open Computer Science, Complex and Intelligent Systems, Microprocessors, and Microsystems journals, SCIE indexed. He is also a member of editorial board of Applied Computing and Geoscience, Elsevier. We welcome you, sir.
Thank you. So today we will discuss about neural network, machine learning, and deep learning. So actually, I will cover all these things in two different presentations, right? And this first one, I'll give presentation on the basis of whatever slides are provided by Nvidia, right? Then after in the next session, it's just after 5 to 10 minutes. So I will cover almost all prevalent things or prevalent technologies which are normally used in machine learning and deep learning, right? Okay, so first we will start with neural net with a single hidden layer. I think all previous slides already covered. Okay, so actually neural, am I audible, Deepa ma'am?
Yes, sir, you're audible.
Okay, then fine. So actually what is actually neural network, right? So neural network is a massively parallel distributed processor made up of simple processing unit which has natural propensity for storing experiential knowledge and making it available for use. So it resembles the brain in a two respects, right? The first thing is the knowledge is acquired by the network from its environment through a learning process. And the second thing is the interneuron connection strength known as synaptic weights are used to store the acquired knowledge. Okay. Third one also we can include, that is the parallel processing, right? Okay. So like our human brain human can many work or many tasks can perform simultaneously, right? You can listen, you can hear, you can also visualize the thing simultaneously, right? Neural network also perform like this, right? So and another thing is that the machine learning. Okay, so machine learning is about extracting knowledge from data, and it is a research field at the intersection of statistics, artificial intelligence, and computer science, and is also known as predictive analytics or statistical learning. The application of machine learning method has in recent years become uh, very popular in everyday life, from automatic recommendation of which movie to watch to what food to order, or which product to buy, to personalize online radio and recognizing your friends in your photos. Many modern websites and devices having machine learning algorithms at their core. When you look at complex websites like Facebook, Netflix, Amazon, it is a very likely that every part of the site contains multiple machine learning models, right? So do you actually there are many times if you talk about a machine learning, if you talk about a deep learning, so there is a learning term, right? So what is actually learning? Okay, so if we talk about a neural network, so neural network normally we can say there are one input layer, and another thing is the hidden layer, and last layer is output layer. Okay, if we talk about a normal single hidden layer, okay, single hidden layer neural network. Otherwise, there are some neural network also who don't have any hidden layer, right? Okay, means just input layer and output layer. So example of that is SOM, self-organizing map, or Conan clustering network. Both are the same thing. So this is the example of only input and output layer. Okay, network having only input and output layer. So if we talk about a learning, so learning may be supervised, unsupervised, and reinforcement learning. Okay. So if we talk about a supervised machine learning, means normally we train our network. Like machine learning algorithm that learn from input output pair are called supervised learning algorithms, because a teacher provides supervision to the algorithm in the form of the desired output. For example, that they learn from likes. So it means whatever data you are using for training purpose, it should have levels for that, right? First you train your network, then you can after training, when training task will be completed, then you can fit any input, right? And you can uh, predict the output with the help of supervised learning algorithms. So example of supervised machine learning tasks like identifying the zip code from handwritten digits on an envelope, determine whether a tumor is benign based on a medical images, detecting fraudulent activity in a credit card transaction. Now we talk about the unsupervised algorithms, the other type of algorithm that we will cover in this slide, actually in next session after completing of these slides. So we will detail discussion of this. Okay. So in unsupervised learning, only the input data is known. No known output data is given to the algorithms. So like there are some tasks or some problems where you don't know the level, right? Okay, so for that, unsupervised learnings play very important role. Suppose identifying topics in a set of blog post, right? So for that, you have to apply unsupervised. Segmenting customers into groups with similar preferences, detecting abnormal activity, abnormal access pattern to a website. Okay. And the another learning is the reinforcement learning, which we'll cover in the next session. Okay. Another this is the you can say the supervised, unsupervised, or reinforced learning, but actually the mathematics behind that. Another thing is that the weight updation. Okay. So I think just a minute. Okay, no problem. We'll discuss. Suppose there is a one input layer. Okay, then another layer is hidden layer. Okay, so and last layer is output layer. Suppose for a simple example we have taken, in hidden layer normally there is a one activation function also, right? So we can say their input layer in, suppose input having a x1 x2 that is xn, right? These are the inputs, and their corresponding weights are w1 w2 that is wn respective. Okay, so the and if any bias is also present, so you can say that is b. Okay, so for the input of the activation function will be x1 w1 plus x2 w2 plus dash dash xn wn plus bias. Okay, this is whatever sum you are getting with the multiplication of input and their corresponding weights plus bias, you will pass through the activation function. Activation function may be threshold function, ReLU function, okay, leaky ReLU, or sigmoid and hyperbolic, just like here, sigmoid, okay. So these type activation function you will use, okay. After that, you will get output. But there is a another term is that what will you do in a for next iteration. So for next iteration, what you have to do, you have to update these weights, right? So for updation of weight, what you will do, so the formula for that is that W new is equal to W old plus delta W, right? Delta W here you can solve with this derivative, okay, with the help of derivative. Otherwise, there are some predefined learning also, right? Like error correction learning, okay, memory based learning, okay, and Boltzmann learning, quantitative learning. So these are the learning types where the value of delta W will change, okay. Suppose if we talk about error correction learning, okay. So for error correction learning, what is the error actually? Error means the difference between desired response and actual output, okay. So that is error, okay. And the weight updation formula for that means that the value of delta W equal to neta means learning rate error, that is EKM, and input XJM, right? So delta WKN is equal to neta EKN XJM. Neta is the learning rate. You can take value like 0.4, 0.6, okay. EKN means the difference between actual output and desired, okay. And XGN is the number of XGN means input, okay. When you will stop weight updation, okay. So I am just describing error correction learning, one of the learning, that is error correction. So when will you stop? Obviously when you will get actual output is equal to desired output, right? It means when you will reduce error. So error is represented by pkn minus ykn, okay. So there is a one term, right, that is called error signal, you can say, okay. So there is a one function of you can say that is represented by 1 by 2 half. It means that half ek square m, that is called mean square error also. For if you are taking only two, there are two outputs, then half ek square and otherwise 1 by m, okay. So your target is what? Reduce this function half ek square n, okay. This is the general architecture. I'm just describing error correction learning, but it is the general things which will be applicable for almost all neural networks. There will be a one function, that is a cost function, right? For error correction learning, the function will be like half ek square n, right? It means you have one function, right? And your target is to reduce, because that function is error function, okay. Means you want to reduce your error. It means you will minimize this error, okay. So for minimizing means you are optimizing, okay. So for optimizing this error, what you will do, you will update the weight of neural network iteratively, right? When you will get optimum result means for after iteration, if you for further iteration you will not able to reduce more, right? It means you will be in an optimum position, okay. I will also discuss about the local minima and global minima. So there other case may be happen, okay. So it means input layer, output layer, and here is a single hidden layer, but for other neural networks there may be other hidden layers also possible, okay. More than one hidden layer also possible. In a deep learning there will be many hidden layers, okay. So it means the gist of this, that there is a one function which reduce means our target or our goal is to reduce or minimize this. Like for error correction learning, it means you want actual output to desired output. For that we can represent some mathematical term, that is half ek square n, where ekn is equal to difference between actual and desired, right? Okay. Or desired minus actual you can do, no problem, because you will square, so there is no impact on that, okay. It will not affect that actually, okay. So for that what we will do, we will perform some optimization technique. One of optimization techniques is gradient descent, okay. For gradient descent, we will differentiate, okay, and we will get the value of delta W. So I think it is clear. Is there any doubt? So you can ask. So this is the complete, you can say, the view of simple neural network, right? Okay, so most of the Nvidia slides are related to the pattern recognition actually. So in early days means before 2012, right? So normally at that time, deep learning algorithms were evolving at that time. So if we talk about speech recognition thing, so for classifier, you have to feed some features, right? So it means your first and ultimate goal is that extraction of features, right? So for extraction of features, so if we talk about a speech recognition, so there is a one concept that is MFCC. Actually, all these terms were taken from research paper. So MFCC actually is a feature extraction using Mel frequency spectrum coefficient. Okay, it's a method of feature extraction of voice signal, and feature extraction is the process of determining a value or a vector that can be used as an object or an individual identity. Okay, so it means you can't feed normal normal machine learning algorithm actually, not deep learning, without extracting features. You have to first extract feature from data, then you will feed to the classifier of machine learning algorithm. Not talking about deep learning actually. In deep learning, there is an inbuilt facility. Okay. If we talk about object recognition, right? So object recognition, yeah, is any doubt? Okay, so if we talk about object recognition, so there are shift hog, k-means, sparse coding, pooling, and classifier, right? So what are the term actually? So if we talk about shift and hog, so these are the feature descriptor, right? So it is a simply feature descriptor is that it is a simplified representation of image that contains only the most important information about the image. So there are number of feature descriptors. Like few are the very popular descriptors are like hog, shift, and surf. And these are widely used, right? So what is hog? Hog, or we can say the histograph of oriented gradient, is a feature descriptor that is often used to extract features from image data. It is widely used in a computer vision task for object detection. Okay, the hog descriptor focuses on the structure or the shape of an object. Okay, and additionally, these orientation are calculated in a localized portion. And finally, the hog would generate a histogram. I think all of you are aware of histogram. Histogram is basically image processing term for each of these regions separately. And the histogram are created using the gradient and orientation of the pixel value. So hence the name histogram of oriented gradient. Shift. Shift help locate the local feature and image, commonly known as the key point of the image. And these key points are scale and rotational invariant that can be used for various computer vision algorithms like image matching and object detection, scene detection, etc. Right? Pooling is normally used for reducing the data size, okay, or reducing the feature map, size of the feature map. So if we talk about a deep learning algorithm, so it's deep. It has a more than one stage of non-linear feature transformation. Okay, so there are various filters we are using nowadays and extracting different level of features like low level, then mid level, then high level, and last trainable classifier. Trainable features hierarchy. So hierarchy of representation with the increasing level of abstraction, each stage is a kind of trainable feature transform. Suppose if we take the example of image recognition. So the smallest unit is that pixel. Okay. So pixel then will extract some features low level features, you will get edge, then you'll get texton. Texton actually introduced by Bella Julius in 1981 to describe the putative unit of pre-attentive human textures perception. Okay, and then motif, then part, and then finally object. Okay, similarly for text, character, smallest unit, then I did other feature, extract that word, then word group, then clause, then sentence and story, and speech also, the sample, spectral band, sound, phone, phoneme, word, normally used in a natural language processing. This one. Okay, so learning representation, a challenge for machine learning, computer vision, AI, neuroscience, cognitive science. So first I'll describe one by one. AI is the simulation of human intelligence process by machine. These processes include learning from constantly changing data, reasoning to make sense of data, and self-correction mechanism to make decision. AI application includes problem solving, game playing, natural language processing, speech recognition, image processing, automatic programming, and robotics. So actually the machine learning is a subset of AI and deep learning is a subset of machine learning. Now we discuss about cognitive computing or cognitive. So cognitive computing is the individual technologies that perform specific tasks that facilitate human intelligence. These are a smart decision support system that we have been working with since the beginning of the internet boom. Cognitive computing refers to understanding and simulating reasoning, understanding and simulating human behavior. Using cognitive computing system, every day we make better human decision at work. Now, what are the difference? So AI augments human thinking to solve complex problems. It focuses on accurately reflecting reality and providing accurate results. Cognitive computing tries to replicate how human would solve problem, while AI seeks to create new ways to solve problem that can potentially be better than human. AI is not intended to mimic human thought and process, but to solve a problem through the best possible algorithm. Cognitive computing is not responsible for making the decision for human. They simply supplement information for human to make decision. AI is responsible for making decision on their own, minimizing the role of human. The neuroscience, machine learning I already described. So neuroscience. So actually deep learning, if we talk about a cortex, right? So deep learning is totally inspired through cortex. I'll discuss next slide. This one. So actually the images, normally images or video or you can say natural scenes are unstructured data. So you can't apply normal algorithms and get very high result, right? Or you can say the accuracy will never be more than 96, 97 if you apply normal machine learning algorithms. So for that, the deep learning evolved. Deep learning actually the you can say the is totally inspired by visual cortex. Visual cortex is related with some our eyes and retina, something like that. So suppose there is a one digit like 504192. For example, we have taken one digit. So if we talk about the human visual system, so human visual system is one of the wonders of the world. Okay. So most people, if we'll write this script, like if I'll write 504192 on this screen, so you can easily visualize, right? Why? Because our human normally identify patterns very easily, but computer can't. Okay. For computer, you have to written very complex algorithm for that. First extract what are the pixels, which pixels are a black and like that. Then extract object. Okay, shape and then object. Okay. then match which digit is like that. So most people effortlessly recognize those digits as 504192. That is a deceptive. In each hemisphere of our brain, humans have a primarily visual cortex, also known as V1. Okay, this one, V1. Containing 140 million neurons with tens of billions of connections between them. And yet human vision involves not just V1, but an entire series of visual cortices like V4, V2, V3 somewhere, okay, and V5, doing progressively more complex image processing. We carry in our heads as a supercomputer tuned by evolution over hundreds of millions of years and adapted to understand the visual world. Recognizing handwritten digits, it is not easy. Rather, we humans are astoundingly good at making sense of what our eyes show us, but nearly all that work is done unconsciously. And we don't usually appreciate how tough a problem our visual system solves, right? So actually, our visual system is too much developed. That's why our human brain can easily identify, right? So it is due to only, you can say, the whatever filters normally used in deep learning, that is inspired by visual cortex. So almost architecture is inspired by visual cortex. So just I already told that it is inspired by, if we talk about a neural network, it is inspired by human brain. Talk about a deep learning or CNN and something like that, it's inspired by visual cortex. Okay. If we talk about other algorithms also, the like bio-inspired algorithms, or we can say the meta-heuristic algorithm, particle swarm optimization, cuckoo search optimization, all these things are the inspired from living things, right? Whale optimization algorithms. Okay. Even there is a one more science that is like you know that speech thing, and you also know that image processing or visual recognition. There is a one more thing that is related with the sound signal processing. That is called olfactory signal processing, and you know that uh, dogs are very efficient to smell and identify the criminals, right? So they know how to identify all these things. So there is a one uh, uh, branch of science that's olfactory signal processing is in a very nascent stage actually. Even I think all of you never heard about that. Okay, so that is the olfactory signal, means smell. Okay, so that is also a one kind of a signal. Okay, that's why dog can identify the criminals from 200, 300 kilometer and trace that you, right? So with that, so it means there are a lot of things which is inspired by natures, right? So the this is the avion third, sometimes referred as to Echelon or the Hule third, was a primitive steam-powered aircraft built by Clemmer Adair between 1892 and 1897, financed by the French War Office. Retaining the same basic bat-like configuration you can see in this figure. The Avion Third was equipped with two engines driving two propellers, while the earlier aircraft had no means of directional control at all. This one was equipped with a small rudder. Trainable features hierarchies, end-to-end learning. So if we talk about the trainable features, so each module transforms its input representation into a higher level one. High level features are more global and more invariant, and low level features are shared among categories. Three type of deep architectures: feed forward, feedback, and bidirectional. If we talk about a feed forward, example of feed forward architecture, multi-layer neural nets, convolution nets. Okay, like CNN are the example of that. Feedback stacked sparse coding deconvolution net is the example of feedback. Actually, deconvolution net is composed of the deconvolution and unpooling layers, not pooling, unpooling layers. And deconvolution is just to convolve the input back to larger size. And last one is the bidirectional. The deep Boltzmann machine stacks autoencoder. Actually, the Boltzmann machine is based on a Boltzmann learning, right? Which is also the type of learning. Three type of training protocols: purely supervised and an unsupervised layer wise plus supervised classifier on top, and unsupervised layer wise plus global supervised fine tuning. So if we talk about a purely supervised, so initialize parameters randomly, train in a supervised mode, training with a stochastic gradient descent using back propagation to compute gradient, normal CNN algorithms, used in a most practical system for speech and image recognition. Unsupervised layer wise plus supervised classifier on top. So train each layer unsupervised, one after the other. Okay, there are different layers. No? Deep learning algorithms. So train a supervised classifier on top, keeping the other layer fixed. And this one is a good when very few labeled samples are available, right? And the last one is unsupervised layer wise plus global supervised fine tuning. So train each layer unsupervised one after the other, add a classifier layer and retrain the whole thing supervised. Good when level set is poor, like pedestrian detection. Do we really need a deep architectures? We talk about all these things written here, just the multiplication of weights and then pass with activation function, the finally we get, right? So in deep learning, there is you will do in a multiple times. Actually, the deep machines are more efficient for representing certain classes of functions, particularly those involved in visual recognition. Because actually, the visual recognition is unstructured data. Okay, so you have to use many layers, right, for extracting different features. So why would deep architectures be more efficient? A deep architecture trades space for time or breadth for depth. More layer, more sequential computation, but less hardware, less parallel computation. Suppose example, we are taking n bit parity, so requires n1 XOR gate in a tree of depth log n. Even easier if we use threshold gates. And if we talk about example 2, circuit for addition of 2n bit binary numbers. So require order of n gates and order of n layers using n 1-bit adder with repulse carry propagation. Require a lot of gates if we restrict ourselves to 2 layers. Which model are deep? So 2-layer models are not deep even if you train the first layer. Like if we talk about RVFNN, SVM, right? So these are not the example of deep learning algorithms. Neural net with one hidden layer are not deep. SVM and kernel methods are not deep, right? Layer 1 kernels, layer 2 linear. But still, this is not the example of deep learning algorithm. The first layer is trained in with the simple unsupervised method ever devised, using the sample as a template for the kernel function. Classification trees are not deep, no hierarchies of features. All decisions are made in the input space. So means for deep learning, it should be some layers which extracting features in hierarchy. So then you can say that this is deep learning algorithm. Are graphical models deep? So there is a one more you can the branch of machine learning that is called probabilistic graphical models. So probabilistic graphical models are a powerful framework for representing complex domain using probability distribution, right? With numerous applications in machine learning, computer vision, natural language processing, and computational biology, right? So whatever here mentioned is that is based on HMM models and its probabilities like minus of p. There is a well-defined formula in that. So actually PGM is a very wide. Okay. So graphical model can be deep and cannot be deep. Deep learning involves non-convex loss function. Okay, so what is non-convex loss function? Actually, what is convex? Convex means suppose I have taken one example of one half ek square n, that is a mean square error. Okay, if we using error correction. So our target is to maximize or minimize this. Our target is minimizing this, right? It means this is the example of convex optimization. Non-convex means we will optimize, but there will be some constraint also for that. Means there is a one equation, there is again the one cost function, as well as there are some constraint also, right? Which are not non-convex. Sorry, which are not convex, right? Then we will say that this is a non-convex loss function. So most of the deep learning use such type loss function, non-convex loss function. Okay. Like convex learning is an invariant to the order in which samples are presented, only depends on asymptotic sample frequency. Human learning is not like that. We learn simple concepts for complex ones, and the order in which we learn things matter. Is about representing high dimensional data. Okay, the data size is high, then you will obviously you will get good results. So there has to be interesting theoretical question there. What is geometry of natural signal? Is there an equivalent of statistic learning theory for unsupervised learning? What are good criteria on which to base unsupervised learning? Actually, for that you have to know a lot of mathematics, right? You have to develop some function and normally some unsupervised learning algorithms designed on the basis of, or we can say the main problem is that optimization, right? Here, if you design any neural network, you have to optimize some cost function, right? For unsupervised also you have to optimize. So for unsupervised, there are Lagrange multipliers normally used like FCM or GCP algorithms. So we normally develop unsupervised learning. We use Lagrange multiplier for optimizing. Okay, so there is a lot of mathematics behind that. Deep learning and feature learning today. So deep learning has been the hottest topic in speech recognition in the last few years. Okay, so if a few long-standing performance records are broken with deep learning methods, Microsoft and Google have both deployed DL-based speech recognition system in their product. Microsoft, Google, IBM, Nuance, AT&T, and all the major academic and industrial players in speech recognition have projects on deep learning. Is you can say the Alexa is also the example of this, right? If we talk about a computer vision, feature engineering is the bread and butter of a large portion of the CV community, which creates some resistance to feature learning. But the record holders on ImageNet and semantic segmentation or convolution net. So deep learning is becoming hot in a natural language processing. Language processing, for example, a speech recognition is the one of example of natural language processing, right? Google Translator is also the example of natural language processing, and you can also design your chatbot using natural language processing. So the connection with the applied math is through sparse coding, non-convex optimization, stochastic gradient algorithm, etc. So in many fields, feature learning has caused a revolution. Handwritten recognition and OCR, face and pupil detection, supervised convolution net operating on a pixel, and hard feature generation selections. Right, so all these are old algorithm actually using in a 2001, 2, 3, 4. Right now we are using a deep learning algorithms. We can produce a better result than these techniques. Object recognition and low res object recognition, road sign, house numbers, early 2010. And speech recognition, deep neural nets for acoustic modeling. Okay. Now we discuss about this. So if we talk about a decision tree. So decision tree is a supervised learning technique that can be used for both classification and regression problem, but mostly it is preferred for solving classification problem. It is a tree structure classifier where internal nodes represent the feature of data set. Branches represent the decision rules, and each leaf node represent the outcome. So we can say that in decision tree there are two nodes, which are decision node and leaf node. Decision nodes are used to make any decision have multiple branches, where leaf node are the output of those decisions and do not contain any further branches. Now discuss about support vector machine. In machine learning, support vector machine or SVM or a supervised learning model with associated learning algorithm that analyze data for classification and regression analysis. The objective of support vector machine algorithm is to find a hyperplane in n-dimensional space. Actually, there are some problem like binary separable. Suppose if you take the example of OR gate, right? So this is the example of it is example of linearly separable, not binary actually, linear separables, right? There are some problems. Maybe there you can't separate using the line, so you can use hyperplane for that. Okay, so n-dimensional RNN. So recurrent neural network. Now we discuss about recurrent neural network. It's a class of artificial neural network where connection between nodes from directed graph along a temporal sequence. This allows it to exhibit temporal dynamics behavior derived from feed-forward neural network. RNN can use their internal state to process variable length sequence of input. This make them applicable to tasks such as unsegmented, connected handwritten recognition or speech recognition. Okay, so RNN widely used in natural language processing. A restricted Boltzmann machine, that is RBM, is a generative stochastic artificial neural network that can learn a probability distribution over its set of input. Restricted Boltzmann machine can also be used in deep learning network. In a particular, deep belief network can be formed by stacking the RBF and optionally fine-tuning the resulting deep network with gradient descent and backpropagation. A deep Boltzmann machine, that is DBM, is a type of binary pairwise Markov random field. Markov random field means that is related with the probability theory, or you can say the Bayesian theorem, with multiple layers of hidden random variable. It is a network of symmetrically coupled stochastic binary unit. Now, discovering the hidden structure in high dimensional data, the manifold hypothesis. So, learning representation of data is like discovering and disentangling the independent explanatory factor. The manifold hypothesis: natural data lives in a low dimensional manifold because variables in natural data are mutually dependent. So, first I would like to explain what is manifold, right? So, in mathematics, a manifold is a topological space that resembles Euclidean space near each point. More precisely, each point of an n-dimensional manifold has a neighborhood that is homeomorphic to the Euclidean space of dimension n. A little bit is more mathematics. Okay. In the simplest way, we can say that the simplest example is our planet Earth. For us, it looks flat, but it is really is a sphere. So it is a sort of a 2D manifold embedded in the 3D space. Okay. Dimension. So in physics and mathematics, the dimension of mathematical space is informally defined as the minimum number of coordinates needed to specify any point within it. Like for example here, all face images of a person. So like suppose we have taken a size of image that is 1000 cross 1000 pixels. So it means the dimension would be like this, 10 raised to power 6. But the face has 3 Cartesian coordinates and 3 Euler angles, and humans have less than about 50 muscles in the face. Hence, the manifold of face image for a person has less than 56 dimensions. Okay, so the perfect representation of face image, its coordinates on the face manifold, it coordinates away from the manifold. Okay, so here you can see the face, not face, pose, lightning, expression, etc. So these are the ideal features. Here you can also check the different view of this image and also the expression. So these are some features. Data manifold and invariance. Some variation must be eliminated. Okay. So actually, this is taken from one research paper, that is dimensionality reduction by learning and invariant mapping. This is the title of the research paper. So in this, the final experiment demonstrate dimensionality reduction on a set of images of single object. The object here you can see, the object is an airplane from the NORB dataset with uniform background. So there are total of 972 images of the airplane under various poses around the weaving half sphere and under various illumination conditions, right? You can check the various illumination conditions. The view have 18 azimuth every 20 degree around the circle, 9 elevation from 30 degree to 70 degree every 5 degree, okay. And 6 lighting condition, 4 lights in various on-off combination. The objective is to learn a globally coherent mapping to a 3D manifold that is invariant to lightning condition. A pattern based on temporal continuity of the camera was used to construct a neighborhood. So this is the description of this manifold. So basic idea of invariant feature learning. So normally we are using activation function for nonlinear things, right? So like ReLU is also the example of nonlinear. So and after that pooling. So here you can check there's a high dimensional feature. So for pooling, the ultimate goal of pooling is to reduce the size of feature. Okay. Here you can check. Okay, so nonlinear dimension expansion disentangling. We are getting this. After pooling and aggregation, we're getting like this, and we can easily separate this data. This one is also the example of. Here one term is using data sparse coding. So sparse coding is a class of unsupervised method. Clustering is also the unsupervised category. Method for learning set of over complete base to represent data efficiently. The aim of sparse coding is to find a set of basis vector such that basis vector normally there are basis function. Okay, so if you study somewhere in a Fourier transform, so Fourier transform is inspired from basis function, or you can say the core of Fourier transform or mathematics behind Fourier transform is a basis function. Okay, so that we can represent an input vector as a linear combination of these basis vector. So this is the you can say the overall architecture: normalization, filter bank, and non-linearity and pooling. Okay, so normalization like variation on whitening, subtracting, average, removal, high pass filtering, and decisive, local contrast, normalization, variance normalization. These are the pre-processing steps normally you can say. Thereafter, the filter bank, dimension, expansion, projection, or over complete basis, then non-linearity, sparsification, saturation, lateral inhibition. And for that, what we will use, we can use some activation function for that, like ReLU rectification, component, wise increase, tan hyperbolic, winner takes all. Winner takes all is basically a competitive learning. Okay, and pooling, you know that. So, okay, thank you. Deepa ma'am. Okay, so I think we can take a 10-minute break, and after that, I'll start from basic and to latest deep learning algorithm. Then I'll share two programs for that, so that you can develop some model. The one is the Celsius to Fahrenheit. Basically, it is based on regression model, and another program is SNMNAST dataset, where you will classify the image. Okay, I think this screen is visual. So after a few minutes, we will start. And from ANN to machine learning, supervised, unsupervised, VGGNet. So I'll cover all these in two programs. So 5 minute break for all. Okay, should we start? So these slides are simpler comparison than previous. So now you can understand too many basic things. Okay, so this is the normal architecture of artificial neural network. So why we are taking artificial neural network? Actually, artificial neural network is the basic, you can the basic of deep learning, or deep learning is inspired from artificial neural network. So here you can see these are the input x1, x2, x3, x. Then there is a one unit that summation and bias. If the bias is present, you can add as a bias. Otherwise, input multiplied by their corresponding weights, right? Means summation of input multiplied by their weight. Okay. So x1 w1 plus x2 w2, x3 w3 plus xn wn, right? Then we will pass through one activation function. Whatever summation you will get here, you will pass through one activation function, right? So here I have taken one activation function, that is threshold or step function, as we can say. So finally we get that is output. Okay. So it means this, if you will using this activation function, means threshold or step function, so you can classify. It means that neural network can be applicable only for binary classification, because there is 1 or 0, right? So it is clear. Talk about a machine learning. Machine learning is set of algorithm that pass data, learn from them, and then apply what they have learned to make intelligent decision. So input feature extractor means we will extract features from input, then we will feed that features to traditional machine learning algorithm. This is a complete scenario of machine learning. It is divided in 3 parts: supervised, unsupervised, and reinforcement learning. Example of supervised, the classification. If we talk about the supervised, so supervised is still categorized in a 2-part: classification and regression. Example of classification is identity fraud detection, image classification, customer retention, diagnostic. If we talk about a regression, so population growth prediction, estimating life expectancy, market forecasting, weather forecasting, advertising popularity prediction. If we talk about unsupervised learning, the example for that, clustering and dimensionality reduction. For clustering, recommender systems, targeted marketing, customer segmentation, dimensionality reduction, big data visualization, meaningful compression, structure discovery, feature elicitation. So example of dimensionality reduction, there is a very well-known algorithm, that is principal component analysis, PC. To talk about a reinforcement learning, so the future is of this learning algorithm, reinforcement learning, right? Real-time decision, robot navigation, running task, skill acquisition, game AI. So if you any doubts, so you can write in chat box, so I can reply, right? So if we talk about a regression, so machine learning model can be classified into the following 3 types based on the task performed and nature of the output. The first one is regression, second is the classification, third is cluster. Regression, the output variable to be predicted is a continuous variable. Example, score of student, right? Or we can say that prediction of stock market. So this is the example of regression analysis, right? Because you have some parameter, on that basis you will predict something. Or you can say there is a one mathematical terms where you will put the value and you will get the output, right? So that is the example of regression. Classification, the output variable to be predicted is a categorical variable. Like example, incoming emails as spam or ham, right? The clustering, no predefined notion of levels allocated to group clustered form. Example, customer segmentation for generating discounts. So if we talk about a supervised learning, there regression and classification, because these are supervised, you will need levels. Levels means training data have some levels. Means suppose if we talk about a iris flowers in data set, having 50-50 samples from 3 species, right? But whatever data set you have of this iris, it is also mentioned for this data set that this is for Virginica, this is for Setosa iris, right? So it means there is a one level for that, right? That is supervised data set. Clustering, for clustering, there is no predefined notion, right? Supervised, example of supervised learning like regression and logistic regression, naive based classifier, k nearest neighbor. K nearest neighbor is based on memory based learning. Decision tree, support vector machine. Unsupervised learning means clustering term means the unsupervised learning. Hierarchical clustering, k-mean clustering, principal component analysis basically used for dimensionality reduction. Similarly, singular value decomposition, independent component analysis also used for dimensionality reduction. If we compare supervised versus unsupervised, okay. So supervised, if we talk about the input, the parameter is input data. So supervised machine learning algorithms are trained using level data. Unsupervised machine learning algorithms are used against data that is not labeled. Computational complexity, supervised machine learning is simpler method. Unsupervised machine learning is a computationally complex, but nowadays supervised become complex. Accuracy, supervised highly accurate. Yes, this one is a highly accurate, and unsupervised less accurate. Reinforcement learning is an area of machine learning. It is about taking suitable action to maximize reward in a particular situation. In the absence of training data set, it is bound to learn from its experience. So if we talk about reinforcement learning, so this is not purely supervised and this is not purely unsupervised, right? So we can understand with this example, reinforcement learning differs from the supervised learning in a way that in supervised learning, the training data has the answer key, means level. With it, so the model is trained with the correct answer itself, whereas in reinforcement learning, there is no level, but the reinforcement agent, right? There is a one reinforcement agent decides what to do, perform the given task. In the absence of training dataset, it is bound to learn from its experience, right? Means there is already one agent which learns, right? So there is no need of supervised learning actually. So how the learning will perform? So we have an agent and reward with many hurdles between, right? There are many hurdles. There is a, here you can see this is the agent, this is a diamond, and these are spire. The agent is supposed to find the best path to reach the reward. Okay, so this image shows the robot diamond and fire, and the goal of the robot is to get the reward, that is the diamond, and avoid the hurdles that are fire, right? The robot learns by trying all the possible paths and then choosing the path which gives him the reward. Suppose the agent is moving towards fire, so we penalize that, like minus 50 marks, minus 12, 20 marks, like that, right? And if moving in the same in right direction, so we will provide positive marks, right? So this is called reward and penalizing policy. The robot learns by trying all the possible paths and then choosing the path which gives him the reward with the least hurdle. Each right step will give the robot a reward, and each wrong step will subtract the reward of the robot. And the total reward will be calculated when it reaches the final reward, that is the diamond, right? So on that basis, we will decide which is the final path. Okay. Gradient descent. Gradient descent changes the weight in a small increment with the help of the calculation of the derivative of the loss function. Loss function may be half ek square and or something else. In a deep learning, there are other loss functions also possible, which allow us to see in which direction to descend. So it means there is a one loss function, you want to minimize that, right? So how will you move? Descend, right, towards the global minimum. Okay, so this is done in a general in a batch or batches of the data in successive iteration of all the data set that we pass to the network in each iteration. Gradient descent is an optimization algorithm used to minimize some function by iteratively moving in the direction of steepest descent as defined by the negative of the gradient. Okay, so a gradient is here you can visualize this thing, right? So suppose if you want to reach minimum, want to lake is in, just you can say the minimum point, right, or optimized position. So gradient is a vector valued function that represents the slope of the tangents of the graph of the function pointing to the direction of the greatest rate of increase of the function. It is a derivative that indicates the incline or the slope of the cost function. Imagine you are in the top of mountains and your goal is to reach the bottom field, but there is a problem. You are blind. How you can come with a solution? Right. So obviously, you will have to take small steps around and move towards the direction of the higher incline. You do it trivially moving one step at a time until finally reach the bottom of the mountain. So this is the example of gradient descent linear regression example. Linear regression means you can separate the points with the help of lines. So this is the optimum solution, and you can check here the cost function is minimized, right? After that, you can't minimize, right? If you will increase more iteration, you are getting the value like this. So there is a one function that is j theta, and we are minimizing using this function. So update the weight or update theta with update rule. So theta minus theta diverges theta by theta. So this is the rule for updating. So we will also use this thing for updating weights. Now we talk about deep learning, machine learning, and artificial. So deep learning is a subset of machine learning where algorithms are created and functions similar to those in machine learning. But there are numerous layers of those algorithms, each providing different interpretation to the data it's feed on. Deep learning, the subset of machine learning composed of algorithms that permit software to train itself to perform tasks like speech and image recognition by exposing multi-layer neural networks to vast amount of data. Right. So here you can see the machine learning is the sub part of AI. Deep learning is a sub part of machine learning. Okay. Deep learning to make sense of something complicated, high dimensional, non-linear big data set, where the model has lots and lots of hidden layers in between and has a very complicated architecture which help us to make sense and extract knowledge from such complicated big data sets. Key difference between machine learning and deep learning. So machine learning always requires structured data like normal data set. Deep learning rely on the layers of the ANN, okay, artificial neural network. Machine learning built to learn to do things by understanding level data. Deep learning, the nested layer in the neural networks, put data through hierarchies of different concepts, which eventually learns through their own error. Last point is very important. Machine learning required human intervention and deep learning human intervention not required. So with this diagram, you can understand with this figure, input this feature extraction, then we feed the feature extracted features to classifier, and then finally we decide this is car or not car. While in a deep learning, it is an inbuilt features inbuilt facility of feature extraction, right? So this is the difference between machine learning and deep learning. The main difference is that human intervention not required in deep learning. So this is one question. If you want to solve, you can just type on chat solution for this. In which of the following application can we use deep learning to solve the problem? Face recognition, sentiment analysis, language translation, all of these. So you can try. Okay, D, yes. Yeah, all of these. That's right. Okay, so all of these. So if is there any difficulty in any in slides, so you can just write. Okay, no problem. I'll try to explain in simpler way, right? Earlier the slides, so in earlier session was the slides was very actually the part of content taken from the research paper, so that content was little bit difficult, right? Now, what is the need of convolution neural networks? So how? Like for example, you can see this is cat, right? What the computer sees, right? We know that this is a cat, right? Okay, you can easily identify, and even I think you don't see these uh, pieces of woods or trees, right? You just identify this is cat. But for computer, it is not easy, right? Even there some part is missing. You this one, which is covered by this, but still you know, right? This is a cat. So this is the beauty of our human brain as our cortex visualization system or visual cortex, right? So computer sees in some numeric form, right? So it is not so easy. Okay. So an image classification model takes a single image and assign probabilities to 4 levels for this cases. A cat, dog, hat, mug. Keep in mind to a computer as shown a figure, image is represented as one large three-dimensional array of number. Three-dimensional means 3D, three-dimensional array of. In this, suppose here cat image is taken 248 pixel wide and 400 pixel tall. This is the size of image, right? And has three colors channel red, green, and blue. So actually, all colored images having a 3 layers: red, green, and blue, right? It means how many number of pixels? 248 into 400. This is the size of one layer. And how many layers? 3. So you will multiply 3 with 3. So 248 cross 400 cross 3 numbers. It means around 2,97,600 numbers. So each number is an integer that range from 0 to 255. So what is the meaning of this? Actually, this is a 8-bit image, colored image, right? So here we are using digital image. So this is a 8-bit colored image. So if the 8-bit color image, it means 8-bit image actually. So how many numbers of gray labels occurs? 2 raised to power 8. Total you will get 256. So because we are starting from 0, so 0 to 255. How many gray labels? 256. So whatever gray labels here mentioned, there are 0 to 255. So it will depend upon what is the bit size of that image. So 8-bit image, right? Okay, so 0 means black and 255 means white. Okay, so these are gray levels which varies values between 0 to 250. Okay, this is the example of these are the example of uh, gray level value, gray level pictures, right? This is the color. Okay, so what are the challenges to identify cat using the computer? Okay, so actually there are some challenges like viewpoint orientation, scale variation, deformation, occlusion, illumination condition, intra-class variation. Right, this you can identify. Okay, but still there is a background filter, but you can identify. But how computer will identify? This is a challenge for that means algorithm. Scale variation also, right? Viewpoint variation. All these are the same, but there are viewpoint variation. Illumination conditions, right? All these are the same objects, but due to illuminations, it looks different if we talk about a computer can't easily identify, right? So these are the some challenges for uh, you can say for algorithms, right? So that's why we need some separate algorithms. So how? So uh, we study on that our human brains and how we recognize these objects. So that's a visual cortex, right? So on that basis, we develop some algorithms that are the CNN, right? So CNN originated from, or we can say that is can inspired from our visual cortex. So convolution neural network or CNN are a specialized architecture. Now we are in a deep learning. Okay, this is the algorithm of deep learning. Okay, CNN are a specialized architecture which work particularly well with the visual data, images and videos. Right, images and videos are unstructured data, so normal machine learning algorithms you can apply, but you can't get good result. Right. So for that, you have to apply convolution neural network. The first convolution neural network, LeNet5, was first introduced in 1998 in paper by Bengio Licon at Boto and Hafner, where it was able to classify digits from handwritten numbers. Okay, so there is a very good story regarding deep learning algorithms or CNN. So actually, CNN are specialized architecture where, okay, and they have been largely responsible for revolutionizing deep learning by setting new benchmarks for many image processing tasks that were very recently considered extremely hard. Although the vanilla neural network means multi-layer perceptron, right? Can learn extremely complex function. If we talk about a simple machine learning algorithm like SVM, RBF, and they can learn extremely complex function. Their architecture does not exploit what we know about how the brain reads and processes images, but still there is a limitation. Right. For this reason, although MLP are successful in solving many complex problems, they have not been able to achieve any major breakthrough in the image processing domain. Okay. CNN had first demonstrated their extraordinary performance in the ImageNet large-scale visual recognition challenge. This is the you can say that there is just like one challenge, or you can say there's a conference like that. Okay, that is known as ILS VRC. The ILS VRC uses a list of about 1,000 image categories, not 1,000 images. 1,000 image categories means there are 1,000 classes, and has about 1.2 million training images. Now you can understand what is the size of data set. 1.2 million training images. The original challenge is an image classification task. Okay, so suppose here you can see this ILS VRC 10 and ILS VRC 11. These are the image uh, net large scale visual recognition challenges. The layers was shallow. Started from here, 8 layers, then 19 layers, 22 layers. Okay, then 152 layers. So, like ILS VRC 13 and the BGG net and LXNet and Google net and ResNet, now the YOLO and etc. So, in figure this, you can now outperform humans having 5% error rate in ResNet. The error rate of the ResNet, a recent variation in the CNN family, is close to 3%. This one. This one is close to 3%. Our human error is 5% to recognize any object, right? But it means the ResNet is far better than our visual cortex system. Okay. Now this is a convolution neural network architecture. So this is a receptive fields: layer 1, layer 2, layer 3, layer 4, layer 5, 6 to 8. Right. So the first layer is responsible for detecting lines, edges, changes in brightness, and other simple features. So how we will detect the edges? For that, there are some filters, right? If you're familiar with image processing, so you know that for that edge detection filters, right? The information is then passed on to the next layer. Because why image processing? Because mostly these neural network have been developed or in processing. There are more deep learning algorithms are coming in the future, right, for visual recognition, right? Why? Because the classification task in images and videos are very complicated, right? Or the result is not too good. We apply machine learning. In layer 2, the information is then passed on to the next layer, which combines simple feature to build detectors that can identify simple shapes, right? First it tracks low-level features, lines, edges, changes in brightness, right? In the layer 2, little bit higher. Okay. The process continues in the next layer and the next, becoming more and more abstract with every layer. And the deeper layer will be able to extract high order features and shapes for a specified object. The last layer of the network will integrate all of those complex features and produce classification prediction, right? The predicted value will be compared to the correct output, where those that are wrongly classified will cause a large error gap and will cause the learning process to backpropagate to make changes to the parameter in order to give out a more accurate output, right? So here you can see this is the input convolution layer, then pooling, then fully connected, then softmax output. Okay, this is general structures using CNN. This is a simplified diagram: convolution, ReLU, pooling. Okay, this is taken from MATLAB. Okay, so here you can understand like data set is flower, cup, car, tree, right? So here I easily classify. I'll describe one by one. Now we will talk about the first layer, that is the input layer. So input layer in CNN should contains image data. You need to reshape it into a single column. It is meaning that suppose you have an image of dimension 28 cross 28, which is equal to 784. So you need to convert it into a 784 cross 1. Okay. First you have to convert into column. Okay. And another thing is that the size of data set should be, all the images should be uniform or same. Okay. So this is the example of convolution layer. So here you can check the image dimension is 5 cross 5. This one is image 5 cross 5. And there is a one filter moving over the image, having a size 3 cross 3. Now the resultant size or a resultant output after convolution is 3 cross 3. So how the convolution operation perform? The value filled in this filters, that is 1, 0, 1, then 0, 1, 0, then 1, 0, 1, written in subscript, right here. So how this operation work? Just multiply with this, like 1 cross 1, 1 cross 0, 1 cross 1, then 1 cross, and whatever you are getting after mission of this, just put it here, right? Like this, enter. Here you can understand better. So is there any doubts you can ask? No problem. You can write. Okay. So here it is written 000. Anyone can explain what is this? Why we have added 000? Actually, the image is this, right? Started from 156, 155, 156. Padding, yes, padding. So in the case of images with multiple channel, that is RGB, the kernel has the same depth as that of input image. So matrix multiplication is performed between KN and IN stack, and all the results are summed with the bias to give us squashed one depth channel convolution feature, right? So actually here you have seen that due to convolutions, the image size is reduced. But we want to retain our motive is not to reduce the size of image. Our motive is to extract feature, right? Using convolution layer. So we are convolving the image. Why? Because we want to extract features from it, right? And the features will depends upon what values you have put it here, right? In filter, right? There are edge detection, line detection. There are various types of filters, right? You just move over the image and you can get that feature, right? So there are 3 layers. So filters move over there, and whatever some you obtained, then after finally get here, then we put it here, right? So I think it is clear from this picture. Now you can better understand. The objective convolution operation is to extract the high level features such as edges from the input image. Convenates means convolution network need not be limited to only one convolution layer. Conventionally, the first convolution layer is responsible for capturing the low level features such as edges, color, gradient, orientation, etc. Then after you are using different convolution layer and activation function, you are getting. So convolution layer also contains the ReLU activation, right? To make all negative value to 0. If you see this ReLU, right? So there is a one disadvantage, right? So input having value less than 0, the output will be 0, right? So this is called rectified linear unit. Activation is the advantages. And if the value, if suppose, and the output will be linear or positive input, right? Computationally efficient allow the network to converge very quickly. Non-linear, although it looks like a linear function, ReLU has a derivative function and allows for back propagation. So why we are talking about a derivative? Anyone? Why activation function should be derivative? Anyone can explain? You can try. There's no problem. Right or wrong, you can try. Just yes, no problem. Why activation function should be derivative? This is a very important thing, right? Because I already told any neural networks there are weight updation. There is a one function where you will minimize that function, right? Or optimize that function. So for that, most of the time we will use some optimization technique. That is like sometime Adam optimizer for machine learning. So Adam optimizer is also the part of the gradient descent. So gradient descent means you are using some derivative terms, right? So if the functions are not derivative, then how will you derive it, right? And another thing is that most of the deep learning network, or you can say the convolution neural network, is based on the back propagation, right? These are a feed forward network, but learning is back propagation. Please remember this thing, right? Learning is back propagation. Another most important thing is the dropout and batch normalization. So there are some regularization technique. In one of that is dropout. So dropout is a regularization technique. On each iteration, we randomly shut down some neurons on each layer and don't use those neurons in both forward propagation and back propagation. Since the unit that will be dropped out on each iteration will be random. The learning algorithm will have no idea which neurons will be shut down on every iteration. Therefore, force the learning algorithm to spread out the weights and not focus on the some specific feature. In other terms, we can say we just drop out some neurons randomly, right? Or deliberately, we can say. In batch normalization, we normalize the input layer by adjusting and scaling the activation. For example, when we have a features from 0 to 1 and some from 1 to 1000, so we should normalize them to speed up learning. If the input layer is benefiting from it, why not to do the same thing also for the value in the hidden layers that are changing all the time and get 10 times or more improvement in the training speed. So suppose if you want to speed up your training, so you should do batch normalization. Another thing is the stride and padding. So what is the meaning of stride? Stride denotes how many steps we are moving in each steps in a convolution like this. Please see this movement of filter, right? So here stride is 1. By default it is 1. We can observe that the size of output is smaller than the input. Okay, so actually decide when you will convolve and the filter will move. So how many, you can say, how many cells we skip, how many cells the filter will skip. Okay, to maintain the dimension of padding, we are talking about a padding. So this is a stride which is related with the movement of filter. Another thing is the padding. To maintain the dimension of output as input, why we want to retain the size of output of convolved image of convolution operation, right? When you convolve, means convolve we want to retain the size of convolved image actually, right? So how we can convolve, how we can do this task, right? So we use padding. So padding is a process of adding zeros to the input matrix symmetrically. Okay. So here you can check. This is the padding 0 0 0 0 0. Okay, so this is the example of padding. So that image size should be same. It depends upon number of pixels you will include in your padding. Okay, so pooling. Similar to the convolution layer, the pooling layer is responsible for reducing the spatial size of the convolved feature. So this is to decrease the computational power required to process the data through dimensionality reduction, right? Furthermore, it is useful for extracting dominant features which are rotational and positional invariant, thus maintaining the process of effectively training of the model. So why it is pooling is needed? First thing is to reduce the feature map, size of feature map, as well as extracting the dominant features. And the dominant features are rotational and positional invariant. This should be noted. So here you can understand pooling. So pooling are two types, the max pooling and average pooling. Max pooling return the maximum value from the portion of the image covered by the kernel. So anyone can guess is there any difference between kernel and filter? Are the same? Kernel, what is kernel? What is filter? And what is mask? Or all these are the same term? Anyone can guess? Actually, kernel is also the filter, synonym of filter, you can see. So max pooling return the maximum value from the portion of the image covered by the kernel. On the other hand, average pooling returns the average of all the values from the portion of the image covered by the kernel. Suppose here 2 cross 2, the size of kernel is 2 cross 2. So first we are performing max pooling. So in this, here you can check 12, 28 and 12. So what is the maximum value for this? The maximum value of we will include all these 4 components or 4 values, we will get 20. Just write here. Then here the maximum value is 30. You write here. Similarly, you will get 112, and similarly you will get 37. Now, if we talk about the average pooling, so you have to average all these 4 values, right? So if you will add, you will get 13. Okay. So first you will add and divide it by 4, actually number of components. So you will get 13. Okay. Similarly, you will get some of these 4 components. You will get 32, and you will divide by 4. You will get 8. Similarly, you will get 79, and here you will get 20 max, and this is the average pool. So max pooling performs as a noise suppressant. So it's discard the noisy activation altogether and also perform denoising along with dimensionality detection. On the other hand, average pooling simply performs dimensionality reduction as a noise suppression mechanism. So max pooling perform a lot better than average pooling. So most of the time we will use max pooling. Fully connected layer. So adding a fully connected layer is usually a cheap way of learning non-linear combination of the high-level feature as represented by the output of the convolution layer. The fully connected layer is learning as possible non-linear function in that space. Why we need to flatten that image? So flattening is simply we want to classify a dense layer, right? So if there are 3 layers, you will convert into 1, just like this, right? So there are 2D matrix. Similarly, we can flatten 3D matrix also. This is a 2D matrix. We just flatten like this. Now you can classify. Another term is the most important, that is a soft max and logistic layers. Why we discuss about a soft max? Because you will use at the last as a last layer of convolution neural network, right? So soft max or logistic, not logistic actually used for binary classification. So soft max we will discuss. So it resides at the end of the fully connected layer, and logistic is used for binary classification, and softmax is used for multi-classification. So this is the example of softmax. This is the formula of softmax classification. Okay, so now you can better understand. Suppose the value of get21, get22, get23 comes out to be 2.33, minus 1.46, and 0.1. Anyhow, we got these values, right? 2.33 minus 1.46, 0.56. Now we will apply softmax here. Okay. The formula for the softmax is that exponential of this value, so exp 2.33, then sum of all these 3, exp of all these 3. So exp 2.33 plus exp minus 1.46 plus exp 0.56. Okay. Similarly, we will perform mathematics or we will get actually output of the softmax. Normally, we in middle layers we will use ReLU activation function, but at last we will use softmax, right? Please note that. Okay, so anyone care what is the any specialty in this, or any unique thing is this? What is the uniqueness? Why we are using softmax? Anyone can describe? Anyone can try? Just try to add, multiply all these things, output. So if you'll add all these 3 output, what you will get? Yes, other can also try. Okay, other can also try. output is sum. Sorry, output is 1. Actually, if sum of all these values, you will get 1. Okay. So what is the advantage? Now you can decide which class will be dominating. Okay. So which having maximum probability value actually is 0.83. It means that object or whatever you are going to classify will belong to class 1. That's why we are using softmax at the last layer. Okay, now we'll discuss about deep learning like AlexNet. AlexNet is also the convolution neural network, example of convolution neural network. So AlexNet is the first deep architecture which was introduced by the one of the pioneers in deep learning, Geoffrey Hinton and his colleagues. It is a simple yet powerful network architecture which helped pave the way for groundbreaking research in deep learning as it is now. Here is a representation of the architecture as proposed. When broken down, AlexNet seems like a simple architecture with convolution and pooling layers, one on top of the others, followed by the fully connected layer at the top. This is a very simple architecture which was conceptualized way back in 1980s. The thing which set apart this model is the scale at which it performed the task and the use of GPU for training. In 1980s, the CPU was used for training a neural network. So another reason is your gaining popularity of deep learning algorithms that we have GPU, right? We have a parallel processor for that, or we have better processor, so that operations are you can operate or you can get result in a speedy way, or complex time execution time is become less. Whereas AlexNet speed up the training by 10 times just by the use of GPU. Okay, so this is the example of AlexNet. You can see there is a pooling, stride, and convolution, right? This is the VGGNet, right? So here you can see the size of image 224 cross 224 cross 3, right? So here convolution plus ReLU. This is source convolution plus ReLU. Red color box showing max pooling and sky blue showing fully connected plus ReLU, and brown this one softmax, right? Last we are using softmax. So VGGNet was introduced by the researcher at Visual Graphics at Oxford. That's why name is VGGNet. This network is especially characterized by its pyramidal shape, where the bottom layers, which are closer to the image, are wide, whereas the top layer are deep. Please. Please mute yourself. Deepa ma'am, please.
DNA டெஸ்ட் சொல்ல போகும் உண்மை என்ன கதையில் ஏற்பட
Okay. So the key idea in VGGNet was deeper network by using a smaller filter. So it is important to note that the small size of the filter is preferred than large filter, right? Please note that point. The key idea in VGGNet was deeper network by using smaller filters, right? It is important to note that the small size of the filter is preferred over than the large filter. Suppose why we are using this is the complete architecture starting from here: input, then 3x3 convolution 64, 3x3 convolution 64, then pooling, then convolution. This is structure like that, and at last there are 3 fully connected layer, and the last layer is software. Okay, so suppose here we have a 5x5 image, this one, and 2 different convolution. We will 2 different convolution, 5x5 and 3x. Filter has the same effective receptive field as that of one of 5x5. If you will use 5x5, it means there are 25, right? So you will get also same output size 1x5. If you apply 3x3, the number of parameters 9, one non-linear activation, 3x3 convolution, and you still get the same result. So that's why we are using same smaller size filters, right? So now we'll practice in Google Colab. So all of you know how to use Google Colab. So I'm just going to share this link. So first log in your Gmail account, then click on this link. Okay. Okay, so please download this file. Now screen is visible to all. All of have you downloaded this file? Okay. First log in your Gmail account, then click on collab link. I shared chat box. Okay, so should I start? Okay, so what we will do, we will try to solve one problem, that is Celsius to conversion of Celsius to Fahrenheit. The formula for that is F is equal to C into 1.8 plus 32. It would be simple enough to create a conventional Python function that directly performs this calculation, but that would not be machine learning. So we will give TensorFlow some sample Celsius value. So what we are doing, so first we will import TensorFlow using command import TensorFlow as TF. All of you can upload your file using from here, upload notebook, and store in drive. Whatever file I have shared, you can download from that. Now import numpy is np and import logging. Right? Numpy is you can say used for array first. Now what we will do, we will train the data. Next step is to train the data. Supervised machine learning is all about figuring out an algorithms given a set of input and output. So now you can understand what is the meaning of supervised. Since the task in this code lab is to create a model that can give the temperature in Fahrenheit when given the degree in Celsius. So we create two lists, Celsius. The first array is Celsius underscore Q, another is a Fahrenheit. Okay. So the value for Celsius is minus 40 and this corresponding Fahrenheit will be minus 40, minus 10, 14, 0, 32, 8, 46.4, 15, 59, 22, 71.6 and 38, 100.4. Right. So this is here you are training your data. Means you know that for this value the output will be like this. Right. Now you can train. Okay. Now we can print what is happening here. For minus 40 degrees Celsius, the Fahrenheit will be minus 40 degree, right? We are not using any formula. These are the real value, right? That means for this minus 40 degrees Celsius, the Fahrenheit will be minus 40. Okay. But we have taken only 3 to 6, 7 samples, right? 7 values. So there are some machine learning terminologies, the features, labels, and example. So features, the input to our model. In this case, a single value, the degree is in Celsius, right? Features means input actually. So what is input for this? Celsius. Labels, the output our model predict. That is level. In this case, a single value, the degree is in Fahrenheit. So pair of examples, a pair of input output used D during training. In our case, a pair of values from Celsius underscore Q and Fahrenheit underscore A at a specific index such as 2270. Now we'll learn how to create a model. So we will use the simplest possible model. We can a dense network, since the problem is a straightforward, this network will require only a single layer with a single name. So we call the layer L0 and create it by instantiating tf.keras.layer.dense with the following configuration. Input underscore shape is equal to 1. This specifies that the input to this layer is a single value. That is, the shape is one-dimensional array with one member. Since this is the first layer and only layer, that the input shape is the input shapes of the entire model. The single value is a floating point number representing degrees Celsius. Units is equal to 1. This specifies the number of neurons in the layer, and the number of neurons defines how many internal variables the layer has to try to learn how to solve the problem. Since this is the final layer, it is also the size of model output. A single float value representing the degree Fahrenheit. In a multi-layer network, the size and shape of the layer would need to match the input underscore shape. So here L0 defined by TF dot keras dot layer dot dense in bracket unit is equal to 1, input underscore shape is equal to 1, which we have defined already. So there is only one layer, otherwise you can also L0, L2, like, right? If there are more number of layers, you can also write. So assemble, next step is assembles layer into the model. So once layer are defined, they need to be assembled into a model. The sequential model definition takes a list of layer as an argument, specifying the calculation order from the input to the output. This model has just a single layer. So that's why we have written model is equal to tf dot keras dot sequential. Okay. First, we will train our networks. For training purpose, we have two arrays, right? In first array, there is the input, and second array, there are corresponding output, right? Then we create the model using tf.keras.layer.dense. Then we assemble the layers using tf.keras.sequence. We can also write in this manner, right? tf.keras.sequential, and here we can define inside. Now we compile the model with loss and optimizer function. So what is loss function actually? I have already described in my slide. That is loss function, like suppose we are using error correction learn. I'm not talking about a deep learning algorithms. So the loss was in that case there is a error. Error meaning the difference between actual and desired, right? So the loss function for that half ek square n, right? That was the loss. Here we can use other loss function, right? So depend upon which model you are using. And if you have a loss function, so their next target is or next target will be optimize that loss. So you will use optimizer function for that. So here we will already define the loss is a mean squared error, which I have already described 1 by n. Okay, pkn minus ykn whole square, right? So I already defined half pkn minus ykn square whole square. That is a mean square. Optimizer here we will use Adam optimizer. That's the gradient based on gradient. Okay, so we have mentioned here model.compile. We are going to compile the model using loss and optimizer. Loss is equal to mean squared error, optimizer is equal to tf keras dot optimizer dot Adam. Okay. Now the loss function and the optimizer used here as a standard for simple model like this one, but many others available. It is not important to know how the specific function work at this point. One part of the optimizer you may need to think about when building your own model is the learning rate 0.1 for this code. And this is the step size taken when adjusting values in the model. If the value is too small, it will take too many iterations to train the model. Too large and accuracy goes down. So finding a good value often involves some trial and error, but the range is usually lies between 0.001 to 0.1. Now we'll train the model. To train the model by calling the fit method. So during the training, the model takes in a Celsius value, perform a calculation using the current internal variables called weights, and output value, which are meant to be the Fahrenheit equivalent. Since the weights are initially set randomly, the output will not be close to the correct value. The difference between the actual output and the desired output is calculated function, and the optimizer function direct how the weight should be adjusted. So now we train the model. So we train the model.fit Celsius, Q, Fahrenheit is input and output, and epochs and verbose is equal to false. For visualization purpose, you can check here. For that, you have to import matplotlib.pyplot SPLT. So here you can check the number of epochs are increasing and the loss is also reducing. Now we try to predict, right? So suppose the cell temperature is in Celsius 100. So for 100 degrees Celsius, corresponding output will be, or it should be 212, but here 211.9953. Okay. So this is the beauty of, you can say, machine learning algorithm. So this is a simple algorithm, so that's why training and testing is very easy or taking less time. So I think it is clear to all. Is there any doubt? Please ask. Any doubt? Please, more interactive. Any doubt? Already I said file, and we are running on Colab because you can use GPU, inbuilt GPU in that, right? Colab. Okay. So we can perform in another way, right? Suppose the first layer is tf.keras.layer.dense unit is equal to 4, input safe equal to 1. Now we are adding more layers. L1, the next layer is L1. tf.keras.layer.dense unit is equal to 4. L2, the tf.keras.layer.dense unit is equal to 1. And because the output is 1, so that's why unit will be 1. Now the model tf.keras.sequential, and earlier we have written L0 because there are 3 layers, so we will write L0, L1, and L2. Same commands we are using, model.combine loss is equal to mean squared error, optimizer tf.keras.optimizer.adam, and by default we have taken value 0. Then we model fit Celsius, Q, Fahrenheit, epochs, where verbose is equal to false. Now we're trying to predict 100 degrees. Okay, so here you are getting 212.000003, right? Little bit more accurate. Okay. So with the help of this example, I think you will be able to solve such type of linear regression problems. Now we'll discuss a little bit more complicated problem. Okay, so first we will install because we are importing data set. Okay, on TensorFlow. So this is the pip install command. Pip install, with the help of pip install, you can install like NumPy and TensorFlow dataset, etc. Right. So we are installing. So this is a classifying images of clothing. Okay. So After that, we will import TensorFlow, right? If you are using in your Jupyter notebook and you have not installed TensorFlow, so first you have to install TensorFlow. Okay. So then you have to import that. So import TensorFlow as TF. Now we will import dataset, TensorFlow dataset. Import TensorFlow underscore dataset as TFDS. Now import math, import numpy as NP, import matplotlib.pyplot as PLT. So we have imported math, numpy, TensorFlow dataset, and tensor. This is for error purpose. Now, what is fashion MNIST dataset? Actually, MNIST dataset contains 70,000 grayscale images in 10 categories. Okay. So the images shows individual articles of clothing at low resolution, 28 cross 28 pixel, as seen here. So fashion MNIST is intended as a drop-in replacement for the classic MNIST dataset, often used as the hello world of machine learning program for computer vision. The MNIST dataset contains images of handwritten 0, 1, 2, etc. in an identical format to the article of clothing we will use here. This guide uses a fashion MNIST for variety, and because it is a slightly more challenging problem than regular MNIST, both datasets are relatively small and are used to verify that an algorithm works as expected. So they are good starting point to test and debug code. We will use 60,000 images to train the network and 10,000 images to evaluate how accurately the network learned to classify images. And you can access the fashion MNIST directly from the TensorFlow. Okay, because this is the inbuilt data set in TensorFlow, so you can use here. So we are using data set as well as metadata also. So we are storing data set and metadata. So in between we can discuss loading the data set, return metadata as well as training data set and test data set. So the model is trained using train underscore data set, and the model is tested again test underscore data set. So here we already divide this data set into train and test, right? So images are 28 cross 28. These images should be uniform. Images should be uniform size, right? Or the first pre-processing step is reshaping of images. The labels are an array of integer in the range 0 to 9. So these correspond to the class of clothing the image represents. Okay. So these are the labels 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 mentioned at the data set, right? So what is meaning of 0? 0 means it is belong to t-shirt oblique top. 1 means belong to trouser. 2 belongs to lower, and 3 means this is dress. 4 means coat. 5 means sandal. 6 means shirt. 7 means sneaker. 8 means bag, and 9 means ankle. So total there are 10 classes, right? So labels will be in numeric form 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So each image is mapped to a single label. Clear? Is there any doubt you can ask? Since the class name are not included with the data set, store them here to use later when plotting the images. So with the help of this function, okay. So we stored in class underscore name with the help of metadata. Now explore the data. Let's explore the format of the data set before training the model. The following shows there are 60,000 images and training set and 10,000 images the test set, right? Actually, this is the inbuilt quality of this data set. 60,000 for available for training and 10,000 available for testing. Total 70,000. So here you can check. Okay, so when you run this program, then you get Number of training examples 60,000 and number of test example 10,000. Now pre-process the step. The value of each pixel in the image data is an integer in the range 0 to 255. For the model to work properly, these values need to be normalized into the range 0 to 1. Right. Suppose if all these images are 8-bit images, right? So gray level will be lies between 0 to 55. What we are doing, we are normalizing these values, and then the gray level will lies between 0 to 1. Okay. So here we create a normalization function and then apply to each image in the test and training data set. So how we will normalize? Using this def normalize images levels and images equal to tf dot cost images tf dot float 30 and images equal to 255 returns images level. Okay. Now explore the process data. Okay, so here we are using command image.numpy reshape 28 cross 28 and figure f plt imso image cmap. Okay, so because here we are using binary, so it is in a binary. So look like this. Grid is false, so that's why there is no grid. So display the first 25 images from the training set and display the class name below each image. So verifying that data is in a correct format, and we are ready to build a train the net. So now we are checking. So here is size 5, 5, 5, and I plus 1. 5 cross 5. 5 rows and 5 columns. So here you can check. Now build the model. The basic building block of the neural network is the layer. A layer extracts a representation from the data fed into it. A series of connected layers results in a representation that is meaningful for the problem at hand. Much of the deep learning consisting of chaining together simple layer, most layers like tf.keras.layer.test have internal parameters which are adjusted during training. So here we are using tf.keras.sequential. Then the layers will be like tf.keras.layers.flatten input underscore save 2828 cross 1, then tf.keras.layer.dense 128 activation tf and dot relu, and then the last layer is a tf.keras.layer.dense 10 activation is equal to tf and dot soft. So anyone can describe why we are using 10. Activation function will be softmax. In middle layers we will use relu, but why we have mentioned 10? Anyone can explain? Yes, 10 classes in a data set. Okay, that's why we have mentioned, right? So there are 10 classes in a data set means the output will be 10, right? So that's why we have mentioned 10. If there are 3 classes, we will mention here 3. And last layer will be soft. This network has a 3 layers: input, hidden, and output. So I have already described in previous program. So tf.keras.layer.flatten. This layer transform the image from 2D array of 28.28 pixel to 1D array of 784 pixel, right? In a column form. Okay. So that's why we are taking first layer as a flatten. Hidden layer are densely connected layers of 128 neurons. So each neurons take input from all 74 nodes in the previous layer. Okay, please note that. And weighting that input according to the hidden parameter, which will be learned during training and output as a single value to the next layer. Output, the TF Keras layer dot dense. If 128 neurons followed by 10 nodes softmax layer, each node represents a class of clothing As in the previous layer, the final layer takes an input from 8 nodes in the layer before it and output a value in the range 0 to 1, representing the probability that the image belongs to that class. The sum of all 10 nodes value is 1. Why sum of all 10 nodes value is 1? Because we are using softmax. Okay, so we are using softmax activation function. So this is the property of softmax function. If you apply softmax function, then the sum of output will be 1. Okay, actually all these are in a probability. Probability, to sum all the probability, you will get value 1. Using softmax activation, a sparse categorical cross entropy has issue and which are passed by the DF that's not related. But because there are multiple class, so that's why we are using sparse categorical cross entropy. Now compile the model. So before the model is ready for training, it needs a few more settings. So these are added during the model compile step. Loss function, optimizer, and matrices. Loss function and algorithm for measuring how far the model output are from the desired output. What it loss function means difference between actual and desired, right? Our goal should be minimize this difference, right? The goal of training is the measure loss. Optimizer, an algorithm for adjusting the inner parameter of the model in order to minimize this loss, right? Matrices used to monitor the training and testing steps. So here optimizer will be atom, but losses we are using sparse category cross entropy function. Just check that I missed something. Okay. So first we define the iterative behavior of the trained dataset. So repeat forever by specifying dataset.repeat. The epoch parameter describe will limit how long we perform training. The dataset dot suffers 6,000. Randomize the order so our model cannot learn anything from the order of that example. And dataset dot batch 32 tells model.fit to use batches of 32 images and levels when updating the model's variable. Right. So batch size is 32. Okay. Now we evaluate accuracy. So let's compare how the model perform on the test data set. First run this program model.fit. Okay, so actually this is a free version, so that's why. I'll start from only at 2 to 5 minutes. Here you can check earlier accuracy was 0.82% and 86, 87, 88. So finally 89% accuracy around. 88 to 89 it will rise. Now we evaluate accuracy. So now we compare how the model performed on the test data set, right? That was training accuracy or testing accuracy. Make prediction and explore. With the model trained, we can use it to make prediction about some images. This command we are using model.predict test underscore images. So the model has predicted the level for each image in the testing set. Let's take a look at the first prediction. So there are some values are given. So anyone can guess what would be the output or what would be the output. There are some values 1.2, 8.3, 1.65, 9.6, 1.0, 2.08, 2.6, 1.01, 2.8. There are 10 values, right? And this describes the confidence of the model. That image corresponds to each of the 10 different articles of blocking. So we can see which level has the highest confidence value. So which highest confidence value? Anyone can guess? Now we will check. 4. So it means cloth belong to this array or this number. Like here we will check which one is 4. 0, 1, 2, 3, 4, 4, right? So I think it is clear. Is there any doubt you can ask? Any doubt you can ask? I also shared this file. You can download. If you any doubt, please unmute and ask, or you just raise your hand. Any doubt related to whatever is covered in my slide or deep learning? regarding image processing, machine learning, deep learning. So you can ask. So I shared Python IPython file, and you can just upload in Google Colab and you can run. Okay.
Yes, sir. Students, if you have any questions, any doubts, you can ask. Sir, I think they don't have any doubts.
Okay. No problem.
Okay. Thank you, sir. Thank you for your wonderful session. It was a very detailed implementation and step-by-step process of deep learning.
Thank you, ma'am.
Thank you, sir. I have posted a feedback and quiz link in the chat box. Participants, please fill that. Thank you, sir.
Can I leave, ma'am?
Yes, sir. Sure. Please fill feedback and quiz. I'll be posting the same link in the Telegram group, so you can take the link from here also.